Hi guys, can everybody hear me?
Yes.
Okay, great, thank you. Okay guys, let's get started. I put up a recorded lecture up on YouTube, and the notes hopefully make some sense. So I'm going to be to sort of start from there, and we're into sort of we're not going to really get too deep into amplifier or otherwise circuit design. We're just going to touch a little bit on it before we move to MOSFETs. So we're just going to sort of maybe have the next couple of sessions on amplifiers, and I think we'll have the midterm next week, probably maybe Tuesday or Thursday, probably Thursday, and then we're just really just going to cover bipolar amps and bipolar devices for the midterm. Okay, so the concept of amplifier, again, we were just looking for something that has a voltage gain, which is basically defined as V out over Vn, and just a swing part of it, not worrying about the bias voltages or the DC voltages that it's sitting on. And we said that the basic way to get that was, as we'd introduced before, a voltage controlled current source and a resistor. So it'd be V and okay, and then this would give us a V out over Vn of minus KRL, and that this part is a voltage to current converter, and this part is converts the current back into voltage. And basically by doing this, by changing I guess one way to look at it is you're sort of changing the ratio of voltage to current conversion on the input and current to voltage version on the output to get your voltage gain, is the way I look at it. And the other thing that we said was that we're not worried about this negative sign. A lot of gain stages are inverting, and we're just really interested in the amplitude being gained up regardless of whether it's positive gain or negative gain. Okay, and then we said that having or using a bipolar transistor, as we've been talking about, it makes a decent voltage controlled current source as long as it's in forward active region, and so that this would be V out. And so this could be our gain element, And finally, that we would have to actually move some things around here to make it a reasonable circuit that would work in the real world, which is basically have the resistor be connected to a high supply. And by the way, we're changing our the drawings a little bit to make things simple. So instead of doing a battery, when I'm talking about a supply, I'm just doing this. So in this case, it'd be something just a line with connecting up to it. And instead of I'm gonna use like a ground symbol for something like this or something like this instead of the bottom rail, basically. So if I do that, we'd end up with something like this with the out, and then the in, and we would have to, again, let me just do whatever input, small signal input you have, but you'd have to bias this up to make sure that this BE, VB, this base emitter junction is forward biased. And we have to make V1 high enough to make the collector base junction reverse bias. Okay. Furthermore, we're going to sort of redefine V output. Whoops. Okay, so let me actually, before I do that, let me just go through all the different definitions we're going to be using. So one is we're going to change, this is just definitions that are typically used in design. So first thing is we're going to call this voltage VCC, which is going back historically, but it's the collecting supply. So if you were using a MOS transistors, that we'll see the power supply will be called VDD for the drain. And so anyway, that's sort of a typical VCC. This guy, we're going to, instead of R sub L, because it's hooked up to the collector, we're going to call it R sub C. Okay, and then we're using this ground symbol for our lowest rail, lowest voltage. And then V output, we're going to define as VCC minus RC IC. So this is the IC on here. So basically what this does is, whoops, why did I just erase that? This basically redefines the output to be with respect to ground rather than with respect to the supply here. Okay, so okay, so that's what, and then we're calling this is a very popular amplifier topology. So amplifier topology, and this is called the common emitter amplifier. And so the reason it's called the common emitter is because the input refers to the emitter, and also the output refers to the emitter. And you could have, as if I don't know if we're going to get to it or not, but because you have these three ports in a bipolar transistor, you have the collector, base, and emitter. You can also have different permutations of amplifiers. So this is a common emitter. You could also have a common base where the input is actually coming through the emitter, and you can have a common collector as well. So I don't know if we're going to get a chance to go into those, but anyway, so this particular one, which is probably the most popular amp topology, is called the common emitter. Okay, let's see. And then if we just do the small signal model of this thing, is our old familiar small signal model. So let's say we want to do a small signal gain calculation, actually small signal. Let me push it out to this guy. Gain. And, you know, just our bipolar transistor real quick is R sub pi, V sub pi plus minus space. So this is a small signal model. G atom, V sub pi, and then R naught for the output voltage, for the early voltage. Okay, and the collector. Okay, so if we, let's, for the sake of ease of discussion, let's say that if we set early voltage to be infinite, that would make R0 R0 would be infinite, so we don't have to worry about R0 for the initial discussion, just to keep things simple, and then we'll add it back in once we calculate the simpler case without R0. Okay, so if we draw the common emitter amp, we would end up having, again, so the input goes to the base of the bipolar. So we would end up having R sub R sub pi, V sub pi plus minus, G sub m, V sub pi, and then there's a whole bit of room here. Let's see, and then, you know, we put in the R sub C here, because this is a collector, and because this is a small signal, we're already assuming the base emitter junction is forward biased, so we're just putting just the voltage source for the small signal from the microphone, say, in this particular case. And the emitter is grounded. And then also, if you remember, we said going from large signal batteries, so this would be large signal, you would assume that anything that is not perturbed is zero. So like basically, this would be a 0 voltage battery, which is basically a short. So that's why we got rid of the biasing element here. And then that's why also why we connect the R sub C to the ground. I just put it up to ground here. Okay, so these are all what's called AC ground. So it's both AC ground, DC ground, and sole AC ground. Okay, so basically coming from that, basically shorting those things out. Okay, so, and then if we just look at the circuit, because VN is directly connected across R sub pi, so V sub pi is just equal to VN. Okay, and then G sub m V sub pi is equal to G sub m Vn. Okay, and G sub m Vn. And that's also equal to, because we have basically the current going through here, we have G sub m Vn is equal to minus V out over R sub C. Okay, so basically V out over Vn is equal to minus Gm R sub C. And this is the gain for the common emitter amplifier. So CE is common emitter amp gain. Okay, so now basically, we can use this as, the idea is you would get to have this common emitter topology as part of your tool bag. So, we need to work it out a little bit more, but whenever you see this common emitter topology or whenever you want to use it, all you have to do is to bias it up properly, and you have a relatively simple equation. You don't need to work out the whole small signal analysis and draw it out. You just know, if I have this topology of the common emitter and you've got the proper biasing going across it, you know what the gain is from V in to V out. And it's basically this. And you do the same thing with the other amp stages, because when you're looking at a complicated circuits with 20, 30 transistors, you want to start training yourself to know. You don't want to write the whole small signal model, the whole start solving KVLs and KCLs for a very complicated circuit. You just want to recognize circuit blocks and do quick calculations what the gains and those kind of profiles are. Okay, so that's the common emitter amp. Let's see. And if we want to, let me see if we want to add this discussion. Okay, so let's say, we have this this circuit, okay? And let's, for the sake of discussion, say that ours is an example. Okay, we had an R sub C of 1 KO. And let's say we calculated the biasing and so on, and we had all that worked out, that the biasing current would be I sub C is 1 milliamp, say. And this supply VCC is 2.5 volts. Okay, so we'd already used this and as an example, and I think we'd worked out that, let's see, let me do it again. So the gain, so GM is with 1 milliamp, it's IC over V sub T, so it's 1 times 10 to the minus 3 over 26 times 10 to the minus 3, or 1 over 26. And the gain is minus GM RC, so that's 1 over 26 times 1 k ohm. And let me just do a quick calculation here. Okay, and so that's about, say, gain of 38 minus. Okay, so we calculated that as the gain under these circumstances. Okay, so let's say that we want to double the gain. We realize this is not enough gain, and we'd like to, again, double the gain of this thing. So this implies, because we've been using, so this is kind of more limitations of what you have to worry about. when you use equations like this, okay? So this implies that you can just say double R sub C to double the gain, okay? So let's see how that would work if we just try to double R sub C. Okay, so let's say we have, whoops, we have R sub C now is 2K ohm, doubled from the previous place. Let's say we kept the input biasing the same so that the current, the bias current is still a milliamp. Okay. And so this should give us, you know, so because the current I sub C is the same, GM should be the same as what we had before. And we've doubled RC, so the gain should be, is AV2 is equal to 2x AV1. Let's say RC2, AV, let's call this AV1, okay? So that's the question we have here. And so the question is, can you do that? And the answer is no, because you know what we'd assumed we'd be able to do is to keep the bias conditions similar. And like, let's take a look at it in this case here. When you're looking at V out, the way we defined it is VCC minus RC I sub C. Okay, so the supply was 2.5 volts. Okay, and RC is now 2K ohm times, we kept the current at a milliamp. And so this is equal to 0.5 volts. Okay, so basically if you look at what we had before was we had in the case of, so case one, we were biased up here at 1.5 volt. And let's say we had a certain gain. And so this is time and V out. Okay. And what we wanted to do was to double this swing. Okay. So we doubled R sub C, but what that did is it pushed our bias point down to 0.5 volts. And so if this would have worked, and then so look at what this did immediately is, you know, to get this base emitter junction biased up here, this guy, so VBE is, let's call it 800 millivolts. So now V out, which is VC, is now less than the base voltage. So now we've reduced V out compared to the base voltage by 300 millivolts. Meaning that we're actually no longer in forward active region. We're in saturation, okay? And what's even worse is if this was going to swing to X, so that's not even the biggest or the lowest point. The lowest point would be sort of the lowest point of your output when it's swinging around. So basically, you know, because we've violated the proper biasing of the amplifier, this is not the case. Okay, so what the problem we have is that the voltage, so-called voltage headroom, and so the voltage headroom is like how much you have, how big is your supply. So VCC is 2.5 volts. If VCC in this particular case was, say 5 volts, we'd be okay. But because it's 2.5 volts, the transistor goes out of saturation. And we talked about the two of the main amplifier characteristics. I didn't mention it this time, but in the recorded, I think I'd mentioned that the two things are voltage gain and power consumption. And you can see that if the power consumption of this stage is, so power consumption, I'm not going to go into that very much, but just describing why the headroom would be limited, is just I sub C VCC, okay? So a lot of times you have a limitation on what this power consumption can be because you're directly draining whatever battery you have and it causes heat and so on. So you can't just, a lot of times you have a limit on what your supply can be and how much current you can run off that supply. So basically you have to worry about that and make sure that your amp is always biased up. And so we have the same problem. Let's say if you try to go and say, you could say, well, I got my gain as minus GM R sub C. So instead of doubling R sub C, let me double GM. Maybe that will solve my problem. And then, but the way you would do that is because GM is I sub C over V sub T, C over V sub T. V sub T is a constant. So the only thing you can do is to double I sub C, or your bias current, to 2 milliamps. And if you double I sub C, you still end up having a voltage headroom problem because V out is VCC minus R sub C, I sub C. And this is 2.5 minus R sub C kept at 1 k ohm, but I sub C doubled to 2 milliamp, and it's the same problem, which is that V out goes to 0.5 volts as your operating point, and that basically takes Q1 into saturation. So I guess again, the lessons there is, yes, you do have this really nice, simple, small signal gain equation, but you have to watch it and make sure that your transistors are always biased properly and the operating point works as you play around with the different options. Okay, so let's say we talked about the gain. Now let's see what would happen. We said when we started working on the CE gain, we said neglect the early voltage. So let's include the early effect. So we're bringing R0 back in. So what this would look like is, again, we have, this is for the common emitter in common emitter, small.
Sorry, Professor.
Yes.
Could you please scroll back up really, really quickly to the example you had earlier? I kind of missed a little bit of the first part.
Yeah, which, is it here, or where would you like?
Oh, just a little bit up, a little bit more, please. Okay, cool.
Yeah, starting with the example. Sorry, that kept moving. Is this where you want to stop?
It's actually a little bit more down. Sorry.
Is it here?
Yeah.
Sorry, there's a little bit of a delay here.
Okay.
So basically the example where we're like sort of draw the R sub C and the 2.5 volt and a milliamp. What was the question?
Okay, that's all. Thank you.
Oh, you just wanted to take it
Yeah,
down.
I just needed to write one of the parts
Wait,
down.
Professor, sorry if
Yeah.
I can jump in. Looking at this, we see that a sub v sub 1, we determine that's equal to negative 38. How does that relate to the second part where we see that at 0.5 volts? What are we?
Oh, sorry. So
There's some
basically what we're
double-
trying to do is we were trying to make, so the goal was we're trying to do this. So we were trying to get to a gain of whatever that ends up being 76, let's say, minus 76. That's what we're trying to do. So trying to double the gain. And so this is the small signal gain. And so this small signal, this equation, the small signal gain equation, just implies that if you wanted to take this guy and get a small signal gain of 76, you could just double R sub C and to get to a small signal gain of minus 76, just using this GMRC calculation. But what we have to make sure is that the transistor stays in bias. So in this case, in this AV1 case, so let's just say the operating point of VO. So if I have time here and V output, and say there's an operating point VO around which we get this small signal gain, is equal to 2.5 volts minus 1 milliamp times 1 kilo ohm is equal to 1.5 volts. Okay, and so this is 1.5 volts as the operating point around which the signal will swing. And because the collector voltage is higher than the base voltage, so this is 800 millivolts, by 0.7 volts, this operating point is good for this amp because the bipolar transistor is in forward active region. Okay, so that we were in a good operating point. But then if we just try to get the higher small signal gain by doubling the resistance, what it does is it takes you out of the good operating point. So it drops this V out, this sort of VO to 0.5 volts. So this is like the large signal behavior. So this is the large signal operating point of the collector voltage, drops it to 0.5 volts, which forward biases the collector base junction, and you're no longer in forward active. This Q1 is no longer in forward active region. So the 1.5 and the 0.5 are the operating points. So these are operating points. Let's call them DC operating points. And this minus 38 and minus 76, that was our goals. Those were the small signal gains at those operating points.
Thank you.
Sure. Any other questions? Yes.
Professor, will you upload the Zoom meeting video to your YouTube?
Yeah. Did you guys, have you guys been getting the YouTubes?
I think just to YouTube from your recording video, something like that. But I do not see any Zoom video.
Any what, sorry?
Okay. I do not see any Zoom meeting video from your YouTube.
Oh, huh.
I think I see it. You have 7 videos, right? Split between art class and 4203.
Yeah. probably.
Okay, so then yeah, I have the link if I can send it in the chat if you guys want.
I'd appreciate that. Thank you.
Yeah. Oh, okay. Okay.
If you kind of start at the Blackboard, and I think I forgot if I'm putting it in under, it's either the course materials or announcements. For each new topic, I try to put in a link for the YouTube video.
I just searched your name and I was able to find it. It was the first thing that
Okay.
popped up. So
Okay, cool. Nice. It's one of the advantages of having a name like Baramek Mansourian. There's no two of us in the world. So cool. Thanks for sending that out. Okay, so if there are no other questions, I'll just get back to this, including the early effect in the common emitter stage. So again, just going to draw the common emitter small signal. And, just notice a couple of things. Again, I've shorted out the battery because we're talking about small signal gain now. This V, I'm drawing it kind of like this compared to this. So it should be trying to be a lowercase Vn, implying that it's small signal. R is lowercase r, again, small signal, R sub pi, V sub pi. And, whoops, let me just like this. Go to the AC ground, which is where the emitter is sitting at. So emitter is kind of sitting on the AC ground. And this is the GM V sub pi. Then that's also connected to this AC ground. And then we had R sub C. So this was like sort of hooked up to, like we had it drawn kind of like that. So I just flipped it over. And from an AC sense, it's connected to ground. This really bothered me when I was undergrad taking these classes. So I wouldn't be surprised if you guys are getting confused, but basically, anything that is not anything that's a DC bias, again here, so we change this DC bias to a 0-volt battery. And so it was as if we had this battery here and DC was 2.5 volts, but in AC, it just looks like a short to ground. Because we're just looking for perturbations. We've already got, information about the bias current and so on from our large signal analysis. So now we're just looking at perturbations. Okay, so we have the R sub C, and then this is again small v out. Okay, so if we add the early voltage back in, so we want to early voltage. So we said, initially it said R0 is equal to infinite. So let's say we don't say that and we add it back in, it'll show up here. And remember that R0 was the early voltage over the collector current. Okay, and this was some specific thing for your bipolar transistor. Okay, so now if notice that these guys are just in parallel. So instead of the gain being just, instead of the small signal gain being minus GM RC, basically it becomes GM RC parallel with R0. Okay, so this is we call this the equivalent resistance of the output. So this R sub C is, a resistor that you actually, as a designer, plugged in on the collector of the bipolar, and R sub 0 is just a part of that transistor that you got from the foundry, and that's sort of the characteristics. So what the early effect does, so early effect reduces the circuit gain. Okay, so adding that, basically just put it in parallel with whatever external resistance you had, but it has the effect of reducing the gain. In fact, as you guys will see, like there's very few parasitics or random things that increase the gain. It's a rule, whatever you want, it's hard to get. So if you want high gain, like everything is like reducing the gain, whatever parasitics and stuff we neglected. Okay, so now let's look at something that's actually a sort of an interview question that I got when I was on my one of my first interviews, which is, well, what happens if you just take the common emitter amp, okay, with your input. (800 millivolts), and you just completely replace the resistor with a current source, with an ideal current source. And an ideal current source has infinite resistance. So I guess the question is, well, if you hook it up like this, you have infinite resistance as your load. What happens? Is the gain infinite, or what is it? So let's take a look at that. So again, I'm going to redraw the small signal model here. R sub pi, E sub pi plus minus. So this is V in, and then we have GM, E sub pi. And then we have the early output resistance of just the device itself caused by the early effect. And then, okay, so now the question is, this is the small signal model. So the question is, what do we do with these, what do we do with the small signal model of a current source? So we said that whenever we're working in the small signal domain, we take whatever's in the large signal domain in terms of supplies and so on, and whatever is not being modulated, we basically zero out. So in the case of a voltage source or battery, this turns into a 0 volt battery, because the DC voltage you zero out, which it looks like a short. Okay, now in the case of a current source, we do the same thing, except so we zero out the current with the current source. Now if you took a current source and zeroed the current, you end up with an open circuit. So the current source model in the small signal ends up being an open circuit to ground. Oops, I need to make this. Okay, which means, because this is open, it just sort of goes away. We don't have to worry about it. So, but basically what happens in this case then is your gain just ends up being just having this component as the resistance, which is the the output resistance caused by the early voltage effects. Okay. And so there's a name, So what this says is that there is a maximum gain that a particular transistor can have. It's called, there's a word for it called intrinsic gain of the transistor. And that's like the max gain you can possibly get out of this device, no matter what resistances you hook up as a load. So this, when you buy a transistor, say, if it's a discrete component, you get basically this is just what you get. This will be defined. So you have the early voltage, and you know how much current you're going to run through it. Oh, by the way, sorry, the current doesn't matter because, like, let's say if I just do this, GM is I sub C over V sub T. Okay, and the early voltage is V sub A, sorry, early, not voltage, the early, the output resistance caused by the early voltage is V sub A over I sub C, so these guys cancel each other out. So you end up with the early voltage over V sub T. So you see, like, this is independent of, sorry guys, AVGM. So this is intrinsic gain, and so is independent of current. Okay, so it's basically independent of current, it's independent of really anything. It's just sort of the intrinsic maximum gain that you can get from that transistor, and it's this early voltage over V sub T. And the only thing that really changes it, I guess, is the temperature. So you'd get a change in V sub T as a result of the temperature. Okay, so so that was all about the common emitter gain stage. Okay, so now let's move on to some of the other things that are important for amplifiers. So now we're talking back on amplifiers in general. So we said one of the key elements was the gain, which is V out over V in. Again, the swings. And we said, you know, the other thing that is power consumption. But, you know, another important effect is the impedances driving basically the input impedance and the output impedance of the amplifier. So input, output, so this is 1, 2, 3. So these are important characteristics. Of the amp. Okay, so let's look at it for the, you know, what this means. And just by looking at the common emitter amp, okay? So we have, again, just redrawing this guy. This is the input. And here's the output. Okay. So the input impedance is sort of like a just a verbal description. Is, you know, for the most part, we're just going to work with resistance. We're not going to worry about capacitive. So complex impedances at this point. So let's just talk about input impedance or input resistance. Is the resistance or impedance you see when you're you're driving this common emitter stage. That means that the previous circuit has to drive this input, and it's some kind of a load. And so the question is, what is that load? And the load that this amplifier puts on the previous stage is important because it's a figure of merit that other previous stage may not be able to effectively drive this stage. Okay, and so the output load, the output impedance is the impedance looking into the output of this common emitter stage or any amplifier stage. And the reason that's important is because the next stage you'll be driving has its own input impedance. And basically this combination of this output impedance of the stage that you're designing and the input impedance of the next stage you're driving has to work, basically. For example, if you have something with a high output impedance and you're driving something with a much lower input impedance, you're going to get a huge attenuation in your signal, and we'll see that. So let's see here. So let's use an example to start looking at the input impedance. Okay, so how should we draw this guy? And okay, so this should be a ground. Sorry guys, terrible handwriting. Okay, so previously what we'd said is, okay, we've got this guy's biasing up the microphone, and whenever we looked at the AC signal of the microphone, this guy, we just said this looks like a voltage source, small signal voltage source, looking at this input. But this isn't a real thing. I mean, if you had a real microphone, this wouldn't be the model for it. What you would end up with is it would have a series, a sort of some kind of an output impedance, some kind of an output resistance. So what it would really look like is sort of real microphone, quote unquote. Because the reason I put it in quote unquote, because even real, we're really simplifying this thing, is Vn plus or minus, and then there is some impedance, output impedance of this output resistance that guy has. Let's call it R sub n for microphone resistance. Okay, so if I put that in this circuit, in this small signal circuit, you'd end up with Vn plus or minus. It would go through this resistance of the microphone. Then you would, then you'd be at the base. Then you'd see the R sub pi, D sub pi minus so again, here I'm just going to ignore early voltage for now. So ignore early voltage, just for ease of analysis. So it means that R sub 0 is infinite. Okay. So, so that's what we have with like a real microphone. So basically, this is our model for the microphone with the output resistance. Okay. So if you look at this, this part, these two resistors, R sub pi and R sub m, just look like a resistive divider. Meaning that V sub pi is no longer equal to Vn. Okay. What it is equal to is Vn R sub pi over R sub pi plus R sub m. Okay. And then we have our old equation, which is V out is minus Gm R sub C V sub pi, which means that minus Gm. So say Gm R sub C, and then I'm going to bring V in on the other side. So this is the gain, R sub pi over R sub pi plus R sub m. Okay, did I get everything there? Yep. Okay, so now basically we took our old gain and we multiplied it by this number, okay? And this number, because it's R sub pi over R sub pi plus R sub m, is a number less than 1. Okay, so basically we lost gain again, so the gain drops. Because of the input resistance, because of the output resistance of the device and the fact that we have a finite input resistance for our bipolar stage. So you can call this an attenuation factor, this drop in gain. And really depends on the ratio of R sub m to R sub pi, okay? So, you know, if say R sub m is roughly equal to R sub pi, then we lose half the gain. And, you know, we saw in the previous examples how difficult it was to get gain, and so to lose half of it because of the input impedance is, you know, really painful. But you know, and then you look at what a typical R sub pi value is, you know, let's again say, again, we assume if I0 or I sub C is 1 milliamp, okay, Gm is I sub 0 over V sub t. So it's 1 milliamp over 26 millivolts. It's equal to 1 over 26. Okay, and R sub pi was just beta over Gm. Then let's say we assume and let's say beta is 100, which is kind of a typical value. So that's is equal to 100 over 1 over 26. So R sub pi in this particular case is 2.6 kilo ohm. Okay, and so depending on the microphone that we use, you know, we don't have control over the microphone. This is like something you're buying off the shelf, and you know, we don't have any control over the microphone's series resistance. So So this is equal. We don't have really any control over this. It's something that we're buying. And this thing is sort of as a general case, if you look at our common emitter stage as a amplifier, so if you draw it as like a triangle, is we have this input impedance. Okay, that we have to try to do something about. Basically, we have to pick either the right input, right type of stage. You know, it's just possible that, you know, a common emitter stage needs higher input impedance, or, you know, it's possible we need to have a lower G sub M or something like that to increase this input impedance. But it's anyway something that's is affecting our gain significantly. Okay, this input impedance, and it's something that we need to worry about. So just because the amplifier has a certain gain by itself without anything realistic driving it, it doesn't mean that that's the real gain in the application. Okay. So that's the input impedance, and sort of a definition of input impedance is, so let's define it. General definition of input impedance is basically, you know, any kind of a two-port network, basically the resistance on the input. Basically, the resistance you see is the input impedance. Okay. Basically, the resistance across the two inputs of any kind of network. Okay. And the procedure to measure it, or to simulate it, or to analyze it, is you would basically you set, whoops, I'll go to shorthand here. So set all independent sources to 0. This is how you analyze it. So it's set to 0. So it means that any kind of a voltage source that's DC goes to a short, and any kind of current source goes to a open circuit. And then we apply a small signal voltage source. Now this is a perfect voltage source between the input terminals. And then we calculate the current supplied by the source. So basically, if you have any kind of black box, you want to figure out the input impedance here. Basically, you set all the independent sources to 0 in your analysis. Then you put in a voltage source, and you measure basically the current being supplied by the source. And the input resistance or impedance ends up being your applied voltage divided by whatever current it's pumping, that it has to pump into the input. Okay, so that's sort of a general procedure. And if we just look at the common emitter. So let me just go to this page. So to calculate, oops. So just let's call it input impedance for common emitter stage. R sub I. And I'm going to be having nightmares about this small signal circuit. I've drawn it so many times today. Vx, so that's our test voltage. And then we have our Ix, which we're interested in. And then GM, V sub pi, R sub C. Okay, so basically I sub x, if you look at this, is current supplied by the source, times R sub pi is V sub pi, but then V sub pi is just equal to V sub x. Okay, so Rn is just equal to R sub pi. So it's a pretty simple equation in the common emitter case. Okay, it's just the R sub pi of the transistor. So one thing to note here is that Rn is not influenced by any kind of the output resistances or the R sub 0 or the early resistance of the early voltage or the load resistor. But it is dependent on the transconductance because GM is equal to, or sorry, R sub pi. Oops. Because R sub pi is beta over GM. Okay, so basically you can, if you reduce the transconductance, meaning that you reduce, and remember the transconductance is I sub C over V sub T, okay? So you could reduce the transconductance by reducing the collector current or the biasing current of your device, and that'll give you a higher input impedance. So that's kind of one knob you have to play with. But then you'll have to be careful that that reduction in I sub C and that reduction in the GM doesn't drop your gain to a value that you can't deal with. That's, yeah, you have to make sure it's still permissible. Okay.
I'm sorry, could you please scroll up really quick?
Sure.
Okay, thank you. That's it.
Okay. Thanks. Let's see. We have 2 minutes. Well, let me give it a shot, at least to describe. So that's input impedance, okay? And it has to do with how well your amplifier can be driven by the previous stage. And then you have this concept called the output impedance. Which is how well your amplifier can drive the next stage. So let's say, again, we're using our common emitter amplifier. And it's being driven by a microphone. And let's say we want this guy to drive a speaker, say. Let's say we draw a speaker kind of, you know, across VCC. Drive it like that. I don't really know what a speaker symbol looks like. Okay. So let's say we're driving that. And then let's say we've got a I sub C0, or bias current is 1 milliamp. Okay, and that, again, we're ignoring the early voltage effect. And so this means that, before we add this speaker, the gain is minus GM R sub C. So let's say that's minus 38 that we calculated previously. So this would be 1 K ohm from previous sample, which is what should end up if you ignore the early voltage and you have a K ohm for your R sub C and a milliamp going down. Okay, so now we've added the speaker to this. Okay, so the speaker has its own input impedance, and it tends to be very low. So I think typical input speaker impede resistances, or again, it's very low. Let's say 4 to 8 ohms or something like that. So very, very low. Okay, so let's say it's 8 ohms, and then we can basically modify our circuit. We got 1 K ohm here. We got 8 ohm here. You can already tell this is pretty bad news. And then we have our microphone here. Okay. Again, I sub C0 is 1 milliamp. Okay, and this is our V out. Okay, so basically, what happens is you got 2 resistors in parallel right here. So you end up, your gain goes from this equation to that equation with R sub C in parallel with, I guess we didn't give that guy a name, so I'll just write it as, sorry. So AV is minus G sub M with your R sub C in parallel with 8 ohms. Okay, and that basically you can just sort of ignore 1 K ohm, and it's in parallel with 8 ohms. So this, I think, gives you something like minus 0.3 X, which is bad news. So you thought you had a gain of 38, but really, after you hooked up your low input resistance load, you ended up with an attenuation. So it went from a gain of 38 to a reduction in the signal by a factor of 3. And so that's, a catastrophic result. So instead of actually gaining up your microphone signal to drive the speaker, you've actually attenuated it, okay? So your option here is to redesign the amp in this case by reducing, because now, your problem was your R sub C in parallel with 8 ohm. So you can drop the R sub C to 100 ohm in parallel with your, in parallel with your 8 ohm. And to get the same gain, you would have to increase I sub C by a factor of 10. And now, so still without the microphone, your A sub B is still minus 38 because we increased, I sub C is 10 milliamps. Sorry. So we reduced the resistance by a factor of 10, and we increased the current by a factor of 10. So the gain without the GM, without the speaker is still 38. And with the speaker, it ends up, because we have increased the GM now went from 1 over, whoops, sorry guys, trying to hurry up too much and slowing down. So GM went from 1 over 26 to 1 over 2.6, increased by a factor of 10 because our current went up by a factor of 10. So the gain with the speaker ends up being 1 over 2.6, 100 ohm parallel with the 8 ohm, okay, which is more like minus 2.8. So at least you're getting some gain. There's definitely a drop in gain, but at least it's some kind of a gain you're getting by reducing your own amp's output resistance to be able to drive something low resistance. But, you know, somewhat you've moved the problem around because, as I mentioned, if you increase I sub C0, you are, you know, you've increased the GM by a factor of 10, means that you've reduced R sub pi by a factor of 10. So you've just reduced your input and resistance. So you have to, you know, it's a problem. You're sort of moving around and you got to see where you are in terms of the resistance of the microphone versus the resistance of the speaker. Okay, guys, I think we can stop there. And I think we're almost done with the common emitter stage. And, you know, we'll talk about some other amplifier structures next time. Thanks.
Professor,
Yes.
do we still have office hours?
Yeah, actually, we don't, but you can just shoot me an email if you want to talk. We can just schedule something, or we can do it over email. Thought that was
Awesome.
that time.
And also, you said for exam to just make sure, is it next week or you still haven't decided?
No, I think we're gonna make it next Thursday. So I think we can. I'm hoping to be finished basically with the bipolar amps, whatever we're going to cover. I mean, we could spend the whole year on bipolar amps, but basically finish what we have time for this coming Thursday, and then use Tuesday for a review or something like that, and then have our test on Thursday, next Thursday. So put it on the blackboard as an announcement.
So, I'm sorry, just like to be clear, like, so we're going to be getting like a review?
Yeah, we're going to be doing a review on next Tuesday.
Awesome. Because if there's a way we can have it like as a study, like last time, like earlier, so there's a way we can have more time to study.
Oh, as a review earlier?
Like a study guide, like the one you did us last time.
Oh, okay, like
that was helpful.
Test or something?
Yeah, so there's a way like we can, if we have it earlier, like we know what's going to be in the exam. Okay. And also like we can like study from it.
Yeah, okay. I'll try to get something like that out for you guys.
Awesome, thank you so much.
Sure.
Professor.
Yeah.
Is the homework a good place to reference for what's going to be on the exam? Because they weren't very related last time.
Yeah. Oh boy. Boy, you know, it's a good question. I'm afraid I'm giving you guys the homeworks that are, you know, covering the topics, but until I started looking at putting the midterm together, I wasn't quite sure what was going to be on it. And so it made sense to put something on it that wasn't quite on the homework. So I don't have a straightforward answer for you. I think the homeworks are like good to do because you're talking about general understanding of the circuits. That'll also help with the midterm, sort of the practice midterm or the midterm itself. But yeah, I'm trying to make a pretty close correspondence between the practice midterm that might be closer than, you know, the homeworks to the midterm.
Okay,
So
thank you.
yeah, so I'm not sure. I can't at the moment. I can't say yes or not. But anyway, whatever we come up with the example midterm will be have a close correspondence.
Thank you, Professor.
Okay, thanks guys.
Thank
Take
you. Have
care.
a good evening.
You too. Bye.
Bye,
Thank you.
Professor.
Oh, thank you.
Thanks.